Just think about the phone in your hand, or the warmth you feel from the sun. Our entire modern world, it really runs on these invisible forces. So today, we're going to pull back that curtain. We're going to explore how a physics puzzle from the 19th century ended up unlocking the secrets to, well, everything from your radio to hospital x-rays.
So let's just start with a question, a little puzzle for you. What in the world could possibly connect a medical x-ray, the signal that's hitting your phone right now, and the simple color red? I mean, they seem totally unrelated, right? But stick with me, because by the end of this, you'll see they're all actually part of the same incredible family.
All right, so our story begins with one of the greatest minds in physics, James Clerk Maxwell. And he was wrestling with this problem, this inconsistency in the laws of electricity and magnetism that just didn't add up.
Okay, so here's the puzzle he was facing. On the left, you've got a normal circuit. You can just think of it like a complete loop of pipe with water flowing through it, no problem. But on the right, you've got something called a capacitor, which is basically like cutting the pipe and leaving a tiny gap. Now the water, or in our case, the electrons, flows up to one side and just stops. So how could the current possibly continue across that empty space? According to the physics back then, it was a broken circuit. But here's the thing, it wasn't. The circuit worked. Something was happening in that gap. And this is where Maxwell's genius just shines. He came up with this brand new idea, a completely new kind of current he called displacement current. He said, look, even in that empty gap, the electric field is changing over time, and that changing field is itself a form of current. It wasn't a flow of particles, not like electrons, it was a flow of energy through a field. And this brilliant idea, this leap of imagination, suddenly made the circuit whole again.
So here's the absolute key takeaway from that. Maxwell realized that this new displacement current, this changing electric field, had to create a magnetic field, just like a regular current of flowing electrons does. And this idea, well, it didn't just fix a small problem in a circuit theory. Oh no, it was the first clue to something way, way bigger about how the universe actually works.
Because think about it, if a changing electric field creates a magnetic field, well, what happens next? This, right here, is the moment a wave is born. It's like a domino effect. It all starts when you wiggle a charge, which creates a ripple, a changing electric field. Now, as we just learned from Maxwell, that changing electric field creates a changing magnetic field right next to it. But here's the kicker. Other scientists had already figured out that a changing magnetic field creates an electric field. So this new magnetic field creates another electric field a little further out, which then creates another magnetic field, and on and on and on. It's this beautiful, self-sustaining chain reaction that just zooms off through space. And what you get is this wave with some really incredible properties. For one, it's transverse, which just means the electric and magnetic fields are waving up and down and side to side, while the wave itself is moving forward, all perpendicular to each other. The two fields are perfectly in sync, peaking at the exact same time. And what's absolutely crucial is that it doesn't need any stuff to travel through. It can go right through the total vacuum of empty space. And as it goes, it's carrying energy and momentum with it.
But here it is. This is the most mind-blowing prediction of them all. When Maxwell sat down and actually calculated the speed of these new theoretical waves using just some basic constants from electricity and magnetism, he got this number, 300 million meters per second. And that number was already famous. It was the known speed of light. And it wasn't a coincidence. It was the answer. Maxwell had just proved on paper that light itself is an electromagnetic wave. He had just unified electricity, magnetism, and light into one single beautiful theory.
You can just imagine this discovery opened the floodgates. Suddenly, light wasn't this one special thing. Nope, it was just one member of a huge, mostly invisible family of waves.
I mean, just look at this. This is the electromagnetic spectrum. You see that tiny little sliver of rainbow in the middle? That is all of visible light. Everything the human eye has ever seen in all of history is in that tiny little band. But look at all the rest of it. From these super long radio waves all the way down to these incredibly short gamma rays, it's a whole universe of invisible energy all around us.
So, what's the real difference between a radio wave that carries the song to your car and an X-ray that can see your bones? Well, fundamentally, nothing. They're all the exact same thing, those self-propagating electric and magnetic fields we talked about. The only thing that changes is their wavelength and frequency. That's it. And that one difference is what determines how they interact with the world.
So you know what? Let's take a quick tour through this invisible reality and just see how these different waves have completely shaped the world we live in today. Okay, first stop, let's start at the long wavelength, low frequency end of the spectrum with radio waves. These guys are the real workhorses of modern communication. They're made just by wiggling electrons back and forth in circuits, and they bring us literally everything from your AM/FM radio and TV broadcasts to the very cell signals that are probably hitting your phone as we speak.
All right, moving up a bit in frequency, we get to microwaves.
Now these are super versatile. We use them for radar systems, for satellite TV, and, of course, for heating up last night's leftovers. Your microwave oven is pretty cool, actually. It works by shooting out waves that are perfectly tuned to the resonant frequency of water molecules, which makes them shake like crazy and generate heat. Next up, we've got infrared, which is something we all feel every single day as heat.
Yep, these are literally heat waves. Any hot object is giving them off. We've harnessed them for things like your TV remote control and for physical therapy. They also play a huge role in the greenhouse effect, helping to trap heat and keep our planet warm enough for life.
Okay, let's take a huge leap now, way up the spectrum to the really high-energy, high-frequency waves. X-rays.
Because these waves have so much energy, they can pass right through soft tissue but get stopped by denser things like bone. And that incredible ability, well, it completely revolutionized medicine, letting us see fractures inside the human body for the first time. Of course, they're also essential for airport security and are even used in radiotherapy to fight cancer.
And finally, at the very, very top of the spectrum, we have the most energetic and powerful waves of all, gamma rays.
These have the highest frequency and the shortest wavelength you can get. They're producing things like nuclear reactions, and we actually use their immense energy in advanced forms of radiotherapy to target and destroy tumors with surgical precision.
So think about that. We went from a simple little puzzle about a gap in an electrical circuit to uncovering this entire invisible spectrum, a spectrum that we now use to communicate across the planet, see inside our own bodies, and even cook our food. It just makes you wonder, what other invisible forces are out there, just waiting for us to find them?